Section: Introduction. In this section, we discuss how modern natural language processing (NLP) systems, especially those involving large language models, start by converting the text we give them into smaller pieces called subword tokens. These tokens come from a big list that was created using special algorithms like byte pair encoding, BPE, wordpiece, or unigram LM. This step is crucial because it decides how words are broken down and understood by the system. We point out that it's not entirely clear how these different methods compare in terms of their effectiveness. Moreover, the tools that people often use to implement these methods, such as Hugging Face tokenizers, sentence piece, and subword NMT, don't always make it easy to choose or understand the best method for breaking down words at the time of use. It's also an open question whether having a perfect match between the method used to create the token list and the method used at the time of use is necessary or the best approach. We provide examples to show that the recommended methods for BPE, unigram LM, and SAGE don't always break down complex English words in the most logical way, even when the right pieces exist in the list. For instance, BPE's method might combine parts of words too early, missing out on better options like ultra and modern. Unigram LM might keep awkward combinations like unprecedented, and SAGE might ignore the clear breaks at the beginning and end of words. In each case, a different method could have done a better job using the same list of tokens. Most of the research up to now has focused on how to build these lists of tokens, how big they should be, and how to make them work for multiple languages. Some studies have looked at how the choice of tokens affects the performance of NLP systems, their theoretical underpinnings, their resemblance to human language processing, or their alignment with the structure of words. However, there hasn't been much comparison of the different methods used to break down words at the time of use across various token lists and using different measures of success. In our work, we set up a careful experiment to see how these different methods affect the performance of 4 tokenizers. We created a set of tests that look at different important aspects. We found that methods which make one choice at a time, which we call greedy methods, actually work quite well across all the token lists we looked at, in terms of both understanding the structure of words and handling information efficiently. Specifically, we saw that SAGE performed exceptionally well by measures that look at word structure, and methods that aim to use fewer tokens did the best in terms of measures related to how humans process language. Now, let's talk about how we define the process of breaking down words into tokens. We consider a vocabulary, which is a list of subword tokens, and a word that we want to break down. We describe a method that splits the word into a series of tokens from the vocabulary in such a way that when you put the tokens back together, you get the original word. This process and its result are what we call segmentation. Currently, the choice of token list and the method for breaking down words are often linked, but we argue that they should be considered separately. Once you have a list of tokens, you should be able to use any method that works best for the task you're trying to accomplish. We then describe 3 simple, or greedy, methods for breaking down words. The first one picks the longest piece from the start of the word that matches something in the list and keeps doing this until the whole word is broken down. The second one does the same but starts from the end of the word. This approach is interesting because it's quite different from how words are usually formed in English, making it a good test for the impact of linguistic structure on these methods. The third method looks for the longest piece anywhere in the word, adds it to the breakdown, and then repeats the process for what's left of the word. This approach tries to keep the word structure intact and has been shown to improve performance in some applications. Lastly, we talk about methods that start with the individual letters of a word and combine them step by step according to rules learned during the creation of the token list. This is how BPE usually works. In our tests, we look at 2 variations of this approach. One strictly follows the learned rules in order, and the other introduces some randomness, which can help bring out less common tokens and improve their representation in the system. This randomness has been shown to enhance the performance of machine translation systems. Section Summary. In this section, we explore the critical role of inference methods in tokenization for NLP systems, which determine how words are represented and modeled. Different methods like BPE, Unigram LM, and SAGE offer unique mappings, impacting the segmentation of complex English words. Our study isolates the effects of inference methods on 4 tokenizers, revealing that greedy methods perform well across various metrics, with SAGE showing state-of-the-art performance in morphological aspects and methods minimizing token counts excelling in cognitive metrics. Section: Likelihood-based inference methods. In this section, we discuss methods for making inferences based on likelihood values. We use these values to segment a word, W, aiming to maximize the total likelihood. Typically, we rely on likelihood values that were determined during the process of building our vocabulary. We consider the likelihood of a segmentation to be the result of multiplying the individual likelihoods together, which is why it's called Unigram LM. Another approach we use assigns the same likelihood value to all tokens, which leads us to choose a segmentation that minimizes the number of tokens. We also introduce an intrinsic benchmark. Often, the analysis of tokenizers involves training language models and assessing their performance on various tasks. However, this method of isolating the effects of tokenization parameters, like the inference method, can be both time-consuming and resource-intensive. It's also prone to instability due to the various sources of randomness in the pre-training and fine-tuning phases of language models. There are few measures that directly apply to vocabularies and their application to corpora, and even fewer that do not mix these measures with the objectives used in creating the vocabulary. Consequently, there's a relatively small amount of research focused on improving tokenization schemes. To address this, we've created and released a benchmark for the intrinsic evaluation of subword tokenizers. We gathered word-level datasets and information measures that are believed to correlate with the performance of language models on downstream tasks. The current focus of the benchmark is on the English language, though datasets for other languages are available. Regarding morphological alignment, we hypothesize that a tokenizer's ability to align word segments with gold standard morphological segmentations is an indicator of how well a language model, using that tokenizer, can represent words. This is particularly true for complex words that consist of multiple roots or morphological affixes. We evaluate our tokenizers using several datasets and compare the generated segmentations with gold standard morphological segmentations, reporting the macro-averaged F1 score across these resources. In terms of cognitive plausibility, we use our benchmark and data to measure how well a tokenizer's output correlates with human performance on a lexical decision task, in terms of both response time and accuracy. We operate under the hypothesis that a good tokenizer will struggle with character sequences that humans also find challenging, and vice versa. We report the average of the absolute value correlation scores across 4 linguistic setups. For token distribution statistics, we report the Rainey efficiency of different segmentations across a corpus. This measure penalizes token distributions that are dominated by either very high or very low frequency tokens. It has been shown to strongly correlate with blue scores for machine translation systems trained with the respective tokenizers. However, recent work has highlighted some misalignments between Rainey efficiency and downstream performance, underscoring the need for an evaluation suite that covers a wide range of domains and disciplines. We also measure the average number of tokens per word across a corpus as a proxy for compression quality and report the proportion of pre-tokens that are segmented differently from the default across this corpus. In our experiments, we evaluate inference methods for several tokenizer vocabularies: BPE, Unigram LM, WordPiece, and SAGE. We use the train split of the mini-pile dataset to construct these vocabularies, with sizes of 32,768, 40,960, and 49,152, using the Hugging Face tokenizers library and identical pre-tokenization at the byte level. Unigram LM and SAGE require an initial vocabulary for their top-down algorithms. For Unigram LM, we use the default implementation of 1 million top n grams, while SAGE was initialized with a 262K size Unigram LM vocabulary. This initial vocabulary also provided us with token likelihood scores for inference. We computed token distribution statistics measurements over the test split of the mini-pile dataset, measuring the RAINY efficiency with an alpha value of 2.5. All experiments were conducted on a personal laptop and completed within several minutes. We present the results of our benchmark for the 40K vocabularies, with results for other sizes and a breakdown of individual evaluation subsets provided in appendices. Section Summary. In this section, we explore likelihood-based inference methods that use individual likelihood values to determine token segmentation for maximizing total likelihood. We introduce an intrinsic benchmark to evaluate subword tokenizers based on word-level datasets and information measures. Additionally, we investigate morphological alignment and cognitive plausibility of tokenizers, and analyze token distribution statistics to understand their impact on downstream tasks like machine translation. Section: Inference Methods. In this section, we delve into the various methods of inference and their performance across different tokenizer strategies. We've discovered that the default or intended strategy for each tokenizer often doesn't perform as well as alternative strategies on certain metrics. Specifically, when it comes to aligning words with their morphological components, methods that rely on merging rules, such as combining I with N, A with M, or O with N, tend to cross morphological boundaries, which isn't ideal. This trend is also noticeable in likelihood-based inference methods, where tokens that appear more frequently are assigned very high likelihood values, sometimes even higher than the values for the correctly segmented words, known as gold standard segments. Interestingly, the strategy that aims to use the least number of tokens not only performs well in reducing the token count, which is expected, but also aligns with cognitive measures. This suggests that people might prefer simpler, more minimal word segmentations. However, we found that likelihood-based inference doesn't do well in terms of RAINY efficiency, which is surprising since improving efficiency is often its goal. On the other hand, dropout strategies align well with their intended purpose by performing well on the same measure. The strategy of using the longest suffix generally shows poor performance, which might be due to the suffix-heavy nature of the English language. This characteristic of English also poses challenges for character-level sequential modeling. It's important to note that these key findings remain consistent regardless of the size of the vocabulary. When comparing different tokenizers, our findings support previous research indicating that byte pair encoding, BPE, doesn't align as well with morphological structures as Unigram Language Model, Unigram LM, does. However, we've identified that some of this discrepancy can be attributed to the method of inference rather than the vocabulary itself. Additionally, we've found that SAGE significantly outperforms other methods in terms of morphological alignment, likely due to its contextualized objective, which helps retain meaningful tokens during vocabulary reduction. Both BPE and WordPiece, which are optimized for data compression, unsurprisingly excel in information measures and, interestingly, also perform well in cognitive benchmarks. This supports previous findings and suggests a correlation between compression efficiency and cognitive benchmarks. Lastly, we observed that the trends within vocabularies based on likelihood are very similar, as are the trends for vocabularies optimized for information. This consistency across different vocabularies underscores the robustness of our benchmark. However, it's worth mentioning that some results are quite close to each other, which could be expected since some inference methods don't significantly alter the sequences of tokens.